Okay, so as I said, this is called lattice energy. And Sheehan, lattice energy, what is a lattice?
A lattice is.
Oh, no.
Oh.
I was setting it up. A lattice is this. For example, if you look at NaCl, sodium is a small ion, chlorine is a big ion, sodium is a small ion, chlorine is a big ion.
How do you know?
No, I'm just explaining what a lattice is. A lattice is the same thing as a crystal. And it shouldn't surprise you too much that because these have opposite charges, that the sodiums are positive and the chlorines are negative, they're really going to hold on to each other very tightly. They're called electrostatic forces of attraction. Now, the definition is something called lattice energy. If I want to do the following, let's say that I want to take a crystal of NaCl and I want to add enough energy to break it up into its ions in the gas phase. That is what I mean by lattice energy. It's the amount of energy in kilojoules needed to change 1 mole of a salt at STP. Notice we always have to specify our starting point, or else we're not certain how much energy we're starting with. And we want to change it to gaseous ions at the normal boiling point temperature. So that's our goal today, is to figure out relatively whether a given lattice needs more energy or less energy. Now, you actually could calculate the exact amount of energy you needed to break up a lattice like this. I show it to you here. It also has a benefit for this reason. If you notice, Q1 and Q2 is the quantity of charge of the, I should tell you something first. You're never responsible for this in this class, but an anion is a positively charged ion. And a cation is a negatively charged ion. So there's a direct relationship, notice, between the charges or the quantities of charge on the different ions and how much lattice energy. So for example, this is a positive 1 and a negative 1 charge. So this would be 1 and 1, 1 times 1. And that would have a certain effect on lattice energy. But clearly, what if I took an ion with a positive 3 charge and an ion with a negative 3? 3 times 3 is 9. Oh my goodness, that's 9 times more. It's a direct relationship. So what we're going to be looking for is when we compare different lattices, those lattices that have charges with big magnitudes have greater lattice energies than lattices with small charge magnitudes. Also notice the radius. That's the distance between the atoms. It turns out that smaller atoms, smaller radii, have a different effect. Because what happens if I have a small denominator? What's the effect on the answer? Do I get a bigger or smaller lattice energy if I have a smaller denominator? Bigger. So if I have a really small number down here, this number becomes gigantic. If, however, I have a big number down here, this number gets very small. So we're looking at two relationships. Oh, Delane, sir, hello. So again, I'm just setting this up. There's a direct relationship between charge magnitudes and the size of the lattice energy. There's an indirect relationship between the size of the ions and the size of the lattice energy. Factors that affect lattice energy. Well, notice, guys, the first place we can look is if we are in a group. So I have 4 salts here. They're all what we call fluorides. And I notice that all of the metals come from group 1. So what changes when I go down a group? Well, notice lithium has 1 shell. The sodium ion has 2 shells. The potassium ion has 3 shells. So clearly I see that I have an increase in the radius. And what do you notice? As the radius goes up, what happens to the lattice energy?
It goes up.
Really?
Down.
Good. 1036 to 923 to 821 to 785. So my friends, as I see an increase in the ionic radius, I'm going to see a decrease in the lattice energy. So if I had to choose which of these salts has the greatest lattice energy, well, the one that's largest has the smallest radius. It's really that simple in terms of radius. The smallest radius is going to give you the greatest lattice energy. Again, the background is that if you're very small, there's very, very little distance between the two ions. If they're closer together, stronger attraction, you need more energy to break them up. And just remember the relationship. Smaller radius, larger lattice energy. Okay. In a group, it's just about the radius. Across a period, things get slightly more complicated. There are two factors at play as we go across a period. What changes? Well, let's take a look first. Oh, you remember from the regular class, as I go across, in this case, fluorine remains the same. We don't look at fluorine because it's constant. Lithium, remember, is a bigger atom. Magnesium is a smaller ion. Aluminum is smaller than that. I don't know if I really did it justice. Let me make this one a little bit larger. So notice, guys, as I go across a period, there's a decrease in the radius. What effect should that have on the lattice energy? If the radius gets smaller, do I get a bigger or smaller lattice energy? Bigger. So a decrease in the radius means an increase in the lattice energy. Okay? Coolness. Now, that's significant, but what we really want to look at is the change or the difference in the size of the magnitude of charges. Well, first of all, notice the fluorine is just a charge of -1. A charge of -1, a charge of -1. The lithium is +1. The magnesium is +2. The aluminum is +3. So if I take the product of the magnitudes, 1 times 1 is 1. 1 times 2 is 2. And 1 times 3 is 3. Ah, that really is what's responsible for this gigantic increase in lattice energy. Again, the more positive the charge, the stronger the attraction, and the harder it is to pull those bad boys apart. So, an increase in the quantities of charge is also going to lead to an increase in the lattice energy. My friends, a little guided practice. Place the following ionic compounds in order of increasing lattice energy. So you'll be given a series of ionic compounds. Rb2O, Al2O3, CaO, and SRS. How do I figure out which of those should have a smaller lattice energy and which should have the largest? Our first order of business is this. First, assign charges to everything. So guys, let's take a moment and assign charges to everything here. Boom, we assigned all of the charges, and we want to calculate the product of the magnitudes. Class, what's 1 times 2?
2.
What's 3 times 2?
6.
What's 2 times 2?
4.
What's 2 times 2?
4.
Okay, so class, based upon that, which of those has the smallest lattice energy?
RBO.
Rb2O, right, that's the least. Which of those has the greatest lattice energy?
Aluminum.
Say it.
Aluminum oxide.
Oxide, very good. But guys, you soon see we run into a problem. We have a tie. CaO and SRS have the same product of the magnitude of charges. So what do? Well, we need a tiebreaker. Boom, egg salad. Guys, we're back. So we said that, not that you thought we were gone, never mind. Anyway, there are two that need a tiebreaker. I have got to figure out whether or not CaO or SRS has the greater or smaller lattice energy. Now notice I chose these in such a way that makes your life very easy. Notice that Ca and Sr are in the same group. Could someone remind us what happens to radius as I go down the group? Does it increase or decrease? Radius. Radius increase. So I have an increase in radius. Oh, but remember, when I have an increase in radius, that means I have to have a decrease in lattice energy. So that means that the smaller calcium actually has a larger lattice energy than the bigger strontium. And notice it works on the other side too. O and S are also in the same group. Again, as I go down a group, ions and atoms get bigger. The radius increases. And as the radius increases, I have a decrease in the lattice energy. So that means the smaller oxygen has a larger lattice energy than the larger strontium. So that means it works in both. They reinforce each other. That means that CaO, smaller ion, has a greater lattice energy than SRS, larger ion, larger ion. So we can finish Al2O3 is greater than CaO, which is greater than SRS, which is greater, of course, than Rb2O. So guys, that's our lesson on lattice energy. I'll see you next time. Say bye.
Bye.
Thank you, Leah.